In the last video, we've seen some examples of maps induced by matrices. As a next step, we want to see how properties and the maps are connected to properties of a matrix and how we can kind of study the matrix to see some properties of a map. Remember that we've seen before that you can study if a linear map is injective, surjective, or bijective by what it does on, if applied to a basis, if we're in the finite dimensional case. And this is what is reflected in the behavior of the matrices actually. And it turns out that now I want to formulate some criteria for injectivity and surjectivity of maps from K to N to K to M by matrices, how you can formulate the same properties that we had before, but this time for matrices instead of linear maps. And we will then see in the proof that it's basically already what we did before. So K is a field. M and N are just natural numbers, and we take an M by N matrix with entries in K. Okay, now we add A1 to AN be the column vectors. So this has M rows, N columns, so that AM1 to AN be the set of column vectors of A. Then the induced map, FA, which goes now from K to N to K to M. This map satisfies the following. First of all, FA is injective if and only if, and this is now a criterion purely formulated by the matrix, the set of its columns, we've seen that this is a part of the vector space which is identified as so isomorphic to K to the M. This is so a subset of K to the M, so to say. This subset is linearly independent. Okay, the surjectivity, there we need that, so FA is surjective if and only if the set of column vectors is a generating set of K to the M. And so here I'm a bit sloppy, of course the set of column, the space of column vectors or columns would be the space of M by 1 matrices, but as I said before, I always want to identify this with K to the M simply by just writing this not as a column but as a vector with coordinates as we used to do. And finally, if we combine this, we get that FA is an isomorphism if and only if, first of all, we already know that we need to have M equal to N. That's a necessary condition to be an isomorphism, and the set of column vectors is a basis of K to the M. And it turns out, if we look at the definition of maps induced by matrices, this is basically, we have seen everything so far, and there's not much to prove. Namely, it turns out, so let E1 to En be the canonical basis of K to the N. And we've seen above, that was remark 8.6, that the columns, 8.6, that the columns of the matrix are precisely the images of these vectors under F. So A1 to AN is the same as F of E1, F to F of En. And we've seen before, the linear maps, the injectivity and surjectivity of linear maps depend on what the map does to a basis. So this is a special case of what we had before, namely this is the case where we just use this basis, this canonical basis here. So it turns out that, we can basically just use statements, I can't write anymore, statements from the previous chapter, where we had these results, what linear maps do to bases and their criterion there. So A, this means, so the map is injective if and only if this, which is the image of a basis, is linearly independent. This is what we've seen in general, so just for general bases and for general linear maps. This is theorem 718. B follows from combining, so we have also seen that if the image of a basis is a generating set, then the map is surjective. So this follows from combining, this basically we've seen that the image of a basis is, or the image of a generating set is always a generating set of the image. And now if the image is then everything, which would mean that this is a generating set of everything, then the image has to be everything. So this follows from combining theorem 710a, so theorems 710a and 715a. So these were the two parts that we just need to combine here. And the same thing then for the isomorphism. This was corollary 719. We have seen that the map is an isomorphism if and only if the image of a basis is a basis of the target space. So this is what we just have right here. So we only need to understand the structure of these maps induced by a matrix, and then we already have it. So this already shows everything we need. Okay, next up we have a nice construction coming on, which is quite important and gives rise to a lot of funny computations. And I'm now doing a hybrid of a theorem and a definition. Theorem definition 8.9. Okay, namely, a very simple thought. So let's take two matrices. So we have L, M, N in N, and we take an L by M matrix. So A, whose entries I denote by small a, ij, be an L times M matrix with entries in K. B, whose entries I denote by small b, ij, a matrix in M times an M by N matrix with entries in K. So yeah, and Fa and Fb be the induced maps. So this is a linear map from K to the M to K to the L, and Fb is now a map from K to the N to K to the M, be the induced linear maps. Okay, now, if we take the composition of these two maps, this goes from Kn to Km, this goes from Km to Kl. So if we take the composition, Fa composed with Fb, this is a map now from Kn to Kl. And a composition of linear maps is linear, so this is a linear map from Kn to Kl. So let me leave some space here. So this goes now from K to the N to K to the L. This is a linear map. And as a linear map between those two, it's again induced by a matrix. So this composition has to be of the form Fc. We've seen every linear map between those spaces is induced by a matrix. So this is induced by some matrix Fc. But what does Fc look? What does this C, this matrix C, look like? And this is what's kind of the theorem part of this theorem and definition, where C is the matrix whose entries I also denote by small cij. This is now and here I'm messing up my blackboard. So this is now an L by N matrix. So first the dimension here, then the dimension there. L times N matrix with entries in K. Whoops, okay. And we can really have a formula for the entries where this matrix C is given by Cij is the following. It's the sum over all from K equal to 1 to M, Aik times Bkj. And this for all I between 1 and L, and all j between 1 and n. Okay, this is the theorem part of this theorem definition. So this is how we can compute this matrix which induces the composition. And now this matrix, C, and this is now the definition part of the theorem definition. This is called the matrix product of A and B, and denoted often by A times B. So this is the product of these matrices. So we get a multiplication of matrices here that we introduce new with the help of this theorem and definition. Yes, so this is the definition part here. Now, we shall see some examples later on, but first we need to prove this thing. So, first of all, something I already mentioned by theorem 7.5, which said that the composition of linear maps is again linear. FA composed with FB is linear. So there must be such a matrix. So C is well defined by theorem 8.5. So meaning this composition is some linear map which always is induced by some matrix C. Okay, and recall it's also, it was part of this theorem by 8.5 that this matrix C is unique. So there's a unique matrix inducing this map, which means this is really, there's only one matrix which has its properties, so this matrix product is actually well defined. Now, so let's do a computation. So, first of all, by definition, so C is just some matrix whose coordinates whose entries I call Cij. So let's just first do the computation. How is FC defined? So FC from Kn to Kl takes a vector in Kn, so coordinates x1 to xn. And now by definition, this is the sum over all j from 1 to n. And now we take xj times the jth column of this matrix. And now to do this explicitly, so the column, fixed column I get if I fix this number j. This is the column index, this is fixed. And so the jth column would be C1j, C2j, and so on to CLJ. This would be the column here as a column vector. And again, I'm identifying column vectors with points in k to the L, so please don't be distracted by that. Now, this is just the formal definition of this map. And now if I kind of use the standard method, so the scalar multiplication just means I multiply everything. And if I take the sum, I can take the sum coordinate-wise. So if I just want to write this in one big vector, this would mean that this would be, in the first entry, this would be the sum from 1 to n xj c1j. In the second entry, I would have the sum from 1 to n xj times c2j, and so on. And in the last row, I have the sum over all x n times c l j. Yes, okay. Okay, this is now just, so far I've done nothing. I've just written down the definition of FC. Now, what I want to do is to write down the definition of this composition here explicitly, and then compare the two results, and then we will see how the coefficients are given there. So what the numbers have to look like, but for this I need to clean the blackboard. Let's compute the composition. So we have FA composed with FB of x1 to xn. So first we apply FB. This means that if we apply FB to this is, the whole thing becomes FA of, and now I'm writing this column vector again as a vector just in Km, don't be irritated, so it's just basically the same written with the commas. As the following, so this is the sum over all j, sorry, not n, yeah, so it's an element of k to the m, and so I have these entries. I hope I just said the right thing. Yeah, anyway. So in the first component, we have xj times b1j, if we just do the same computation as before for the matrix C. In the second component, we get the sum over all xj b2j, and so on, until finally we get the sum over all j from 1 to n, xj bmj. Okay. Now, by definition, if we apply fa to this thing, so fa means these are the coefficients with which we multiply the column vectors of A. So technically, now I'm writing this again as a column because that's more convenient in this setting. This is the sum over all k equal to 1 to m of the kth entry of this guy, of these guys here, meaning this would be the sum from 1 to n xj bkj. Okay, this is the kth coefficient, kth entry of this vector, times the kth column of the matrix A. And then a kth column of the matrix A is then a 1k, a 2k, and so on until a lk. Now, if we just multiply this and bring things together here, it's the same as before. We can just multiply each component of this vector separately and then take the sum in each of the components. This is just component-wise. So this, in the end, is just the same as the sum, and now this becomes a bit messy. The sum from 1 to m of this coefficient here, the sum j from 1 to n, xj bkj, times a 1k. In the second entry, we have the same stuff with a 2k, a 2k, and so on. And in the end, we have the sum from 1 to n of the sum from 1 to n xj bkj times a to l. Okay, and if we just reorder the things there a bit, okay, this takes a lot of space actually. Okay, this is the same, because here we can just kind of rearrange the sum. This is basically one way of summing all these elements here in this product here, but if we just factorize this inside the sum, so we can, of course, this interchanges with the summation, so we can just put this ak in there. This is the same as the double sum from k from 1 to m and the sum j from 1 to n xj times a1k bkj to the final entry sum from 1 to m, sum from 1 to n, xj times al. Wait, somewhere I did, oh, sorry. This is alk. I'm sorry about that. This was, of course, alk. I was just a little confused. No, okay. alk times bkj. Whoops. Okay, and now, since this is, so this is a sum of finitely many elements, and this double sum is basically one way of summing them all up. And since these sums are finite, we can just interchange the order of the sums. And then now taking a shortcut, I can just go from k in the second sum and from j in, over j in the first sum and do the same here. Simply because everything here is a finite sum. And now I see that the inner sum is over k, and this first factor xj does not depend on k. So I can just, this is like inside this inner sum, this xj is like a constant, so I can just pull this out of the sum. Meaning this is the same as the sum over all j from 1 to n of xj times the sum over all k equal to 1 to m a1k bkj until in the end here, in the final entry, we have the sum from j equal to 1 to n of xj times the sum over k, a, l, k, b, k, j. Okay, and now comparing this with the previous formula, we've seen, maybe let me add this here. This should be the same as this map FC that we had before, and the formula from before, which is not on the blackboard anymore. This looked like sum j from 1 to n xj times c 1j to the sum of all xj times c lj. Okay, and if we now compare these sums, we see that this can only be satisfied, and this can be basically checked by putting in some various values for the xj, but this equation holds for all x, and this can only be the case if this coefficient is the same as this, and so on, meaning Cij must be the same as the sum from 1 to m over k, a1, k, b, k, j, for all I and j. And this is what we wanted to show. So this is indeed, if we just compare them, this is the matrix. I hope I didn't get you totally confused by these indices, but yeah, this is basically the idea is straightforward computation. Now, this is the matrix product. So this is, we have now identified the matrix which gives the composition. And before I do an example of the matrix product, let me give some remarks, some very basic remarks on this matrix product. Okay, we take L, M, N in N, whoops, A to be an L by M matrix, B to be an M by N matrix. Okay. Now, first of all, we had this shorthand notation for these maps FA. So in shorthand notation, so the composition, so what we've shown previously was that the way we defined our matrix product, this composition here is the same as f of this matrix A times B. And in the shorthand notation that we had before, this is the same as just having, so we had denoted this FA of V simply by A times V, or just AV. And now if I apply first FB and then FA, this becomes ABV in this shorthand notation. So this is just the same as this. And this here in shorthand notation would just be A times B V. So this is a nice way of memorizing this. So basically it looks like we're only, actually what we're doing is only multiplying matrices, but here you can see kind of some, it looks like we're like an associativity condition, and this is what it is, essentially. So this holds for all V in Kn, and this is a nice way of memorizing this as well. Now, also just speaking of shorthand notation, one often just leaves out the dot instead and just writes AB instead of A times B, same way as we do this for numbers, right? We always leave away this multiplication dot, and so this is what we can also do for matrices. Now, okay, this is shorthand notation. First of all, keep in mind, this is something I had only said. So some product is well defined, and this, you cannot just multiply arbitrary matrices, but the rows and the columns need to coincide. So if, what do we need in particular? We need that the number of columns of A, is the same as the number of rows of B. Otherwise, this doesn't make sense because they kind of map to different spaces, so this composition there wouldn't be well defined. So in our case, this is really necessary, and this is unfortunately some common mistake that people multiply matrices that you cannot multiply. So otherwise, this just doesn't exist, this product. So this is the necessary condition here. Now, so how do we compute these things? Just let me put this also in as a remark. The ij entry of the product of A and B, so the one with the ij coordinate, how is this obtained? So let's take a look. There's still the equation. So this would be the formula. So, oh sorry, I made a mistake here. This should have been an I. Sorry about that. So if we take these terms here, which are multiplied and then summed up, what does happen here? So here we have the entries AI1, AI2, AI3, and so on. These are occurring. This is the ith row. So we take the elements of the ith row of A. So by multiplying, I'm just doing this very vaguely. I'll give you an example in a bit. By multiplying the entries of the ith row of A, so with some entries of the matrix B, and let's take a look at which ones do we have. This is BKJ, so B1J, B2J, and so on and so on and so on. These vectors, if you take a look at the matrix, these are the vectors from the jth column. So here the other index is fixed. So by multiplying the entries of the ith, and what we always do is we take kind of the first entry of the ith row and multiply it with the first entry of the jth column here, then take the second entry of the ith row, multiply it with the second entry of the jth column, then the third with the third, and so on and so on and so on, and then sum them all up. So we multiply the entries of the ith row, and let me just write this 1 by 1 with the entries of the jth column of B, and then summing them up. And this is something which is actually not very difficult. You just have to get used to it. And this is what we will do by computing an example, and you will also get a lot to do of this, or stuff to do with this in the homework. And let me just write down the matrices here, since this is taken an unreasonable amount of space. Let me just write down which matrices I'm going to multiply. So we take the following matrices. A should be a 3 by 3 matrix. 3 by 3 matrix with real entries. So really, let's consider really some numbers. And we take a 3 by 2 matrix. Whoops. With real entries, which are given as follows. A is the matrix 2, 1, minus 3, 1, 0, 5, 3, minus 1, 4. So this is a 3 by 3 real matrix. And B is supposed to be the following matrix. So this is 3 by 2, so it has 3 rows and 2 columns. 1, minus 1, 4, 2, and 7, minus 2. So what we want to do is now, so we want to compute, so we want the product A times B. Now, to check this is well defined, this has 3 columns, this has 3 rows, so it's well defined. If we would consider B times A, this is not well defined. Because if we would consider B times A, the number of columns of B would need to be the same as the number of rows of A. This is not the case. Here we have 2, here we have 3. So B times A is not well defined, right? So this is, yeah. So in this case, it's not like with numbers where you have commutativity, so that A times B is B times A or something always. This is definitely not the case for matrices for this multiplication, so don't get distracted by that or don't erroneously do it. Now, okay, now since I have taken an uneconomic amount of space, I already need to erase again, but then I will show you how to do this explicit scheme of how to multiply these matrices. See you after erasing. Okay, I have prepared a little scheme by which we will compute the matrix product, and now doing this in very excessive detail because this is our first time computing a matrix product. So this will be our final matrix here. And here I've denoted on the left-hand side, I've put the rows of A. These dashed lines are just there to give us orientation. They don't mean anything, it's just to give you an overview. So first row of A, second row of A, third row of A. And here on top, we've got the 2 columns. We have the first column of B. So this is the first column of B, this is the second column of B. And now we will use them by the recipe I just sketched in the remark to compute the entries of the matrix. So, as I said, we need to compute basically the products of the rows of A with the columns of B, so to say, and this means the following. We start here with the top left corner, so this top left entry. Remember, the result is a 2 by 3 matrix, as is indicated here by the dashes. So this top left entry would be obtained by taking the first row of A, the first column of B, and then multiplying the elements one by one and taking the sum. So, concretely, this means we take the first entry here, the first entry there, and multiply them, 2 by 1. Then we add the product of the second entry here multiplied with the second entry there, which is 1 times 4. And finally we get here, we add minus 3 times 7, which is minus 21, or minus 3 times 7 to do this very explicitly. Okay, now the second entry on the left-hand side, we take the second row of A and the first column of B. So we do the same thing, 1 times 1 plus 0 times 4 plus 5 times 7. Okay, third row, same game. Here we are in this entry, we take the third row of A and the first column of B. So this is 3 times 1 minus 1 times 4 and finally plus 4 times 7. Okay, and on the right-hand side here, we need to do the same thing with the 3 rows of A, but this time taking the second column of B. And if we had more columns, of course, we would do the same thing over and over. So here in this entry, we need to take the first row and the second column here, which means we take 2 times minus 1 plus 1 times 2 plus minus 3 times minus 2 minus 2. Okay, this entry here takes the second row of A and the second column of B, which means we get 1 times minus 1 plus 0 times 2 plus 5 times minus 2. And finally, here we need the third row of A and this column, so we get 3 times minus 1 plus minus 1 times 2, so minus 1 times 2 plus 4 times minus 2. Okay, and now we just need to compute these sums in order to obtain our matrix, which is basically high school mathematics now. So we obtain that the product A times B is given by, so let's see, in the first entry we have 2 plus 4, which is the 6, minus 3 times 7, minus 21, and 6 minus 21 is minus 15. Okay, this entry we have minus 2 plus 2, this cancels out, and here we have minus 3 times minus 2, which is plus 6. Here we have 1 plus 0 plus 35, which gives 36. And here we have minus 1 plus 0 plus minus 10. So and minus 1 minus 10 gives minus 11. Okay, third row, here we have 3 minus 4, which is minus 1, plus 28, which gives 27. And finally here we have minus 3, minus 2, which is minus 5. And here we have minus 8, so in total minus 13. So this is our matrix product that we were searching for. Okay, this is how we compute a matrix product. I hope this example made things clear to you, and yeah, you will have to compute some matrix products in the exercises, so you will also get hopefully some intuition about this, and yeah, we'll be able to compute this. Okay, so from computations back to the dull theory. I want to explore some properties of this matrix product and of this multiplication of matrices. So let K, L, M, N be natural numbers, and now assume in part A that we have 3 different matrices. So let A be a K by L matrix, B be an L times M matrix, everything of course with entries in the same field K, C be an M by N matrix. Okay, now if we first multiply A times B, this is well defined because this has L columns, this has L rows, fine. So this gives us a K by M matrix. And this has M, so the product then has M columns, and this here has M rows. So we can multiply this with C. So take the matrix product of this result with this. Then this is indeed the same, and now you are probably guessing what's happening, as taking the product of A with the matrix product of B and C, but first I'm doing this multiplication, then that. And this is really non-obvious. So of course for multiplication in the field we have this, we know this by definition, but for the matrices this is not clear at all. Okay, and B, part B finally, this is, this is very short, so I'll put this here below. So let now A be some M by N matrix. Then we have seen the identity matrices. Those were the matrices which had only 1 in the diagonal entries there and 0 everywhere else, and they represented the identity as we saw. So here it turns out that A multiplied with the identity N matrix, so of size N, is the same, multiplication with the identity matrix is just A, and this is the same as multiplying from the left-hand side with the identity matrix, except now we have to take the matrix of size M, since this is kind of, this is an M by N matrix. So these are both same. So this is, the identity matrix is in some sense a neutral element for multiplication, so to say. So they behave as nicely as we want. Wait, yes, this is wrong way, right way around. Okay, how do we see this? So there are 2 ways of doing this. The first one, I would give an exercise as an exercise to you, because that's a nice, it's not nice, but it's kind of probably very insightful, namely doing the brutal computation here. So computing the entries of this, multiplying this. I mean, we have the product defined. We just have to compute this product here, compute this product, and check that they are the same. Okay, this takes a while, but this is possible. This is totally elementary possible. And the same way here, we can just compute the matrix product with the identity matrix just right from the definition. But there is a nicer way of seeing this, namely to go via the maps that are induced by these matrices. Namely, so part A, we have seen before, so by theorem definition 8.9, where I introduced the matrix product. So the idea and the definition of the matrix product was so that the product of the matrix would induce the map, which is the composition of the maps induced by the individual matrices. So by this theorem definition, we know that A times B induces FA composed with FB. So then hence if we take the product of this with C, this will be the, this induces the composition of the map induced by AB, which was this, with the map induced by C, which is simply FC. Okay. And similarly, we can do the same thing on the other side of the equation for the matrices. We can take the other way of putting parentheses in here. So similarly, A times B times C. This would be the composition of the map FA with the map induced by this product here. And this is FB composed with FC. So these are the 2 maps that we have to compare. And we know that the composition of maps is associative. Composition of maps is associative. We know that these 2 are the same. So this composition here is the same as this composition. Okay, and we've seen that the matrices representing a map are unique. So this represents this and so, induced this, sorry. This map induces this, this matrix induces this, and the other matrix induces this. So uniqueness, I'm just writing in here, this means that the matrices have to be the same. So A times B times C must be equal to A times B times C, with parentheses put the other way. Okay, so this is kind of the smart way of showing this without having brutal computations to do. But you're, of course, invited really to do the computations for yourself and check right from the definition of the matrix product from its properties that, yeah, you can really obtain this by explicit computations. Part B, similar idea. In, so the identity matrix of size n, we've seen that the map induced by this matrix is the identity on Kn. And of course, Im induces the identity on Km. This we've seen in example 872. Okay, so from this we can discuss by again using this theorem 8.9 that the product of A with In induces then the composition of the maps which are induced here. So this is Fa composed with the identity of Kn. And in the same way, the other product, Im times A induces the composition of the maps induced by these matrices, induces the identity on Km composed with Fa. But we know that Fa composed with the identity. So the identity does nothing. So composing with this identity map doesn't change anything, which means this is the same as Fa itself, and it's also the same as putting the identity map on the other side, because if we just afterwards put in there the identity, this is totally irrelevant as well. So this doesn't change anything. So this means, so this here is induced by A times In. This here is induced by Im times A, and this is of course induced by A. So again, by the uniqueness of these matrices, which induce a map, we get that A times In is equal to A, and this is equal to Im times A, which concludes the proof. And again, you could have done an explicit computation and obtained the exact same result here. Okay, now we have studied these matrices so far, and the next thing in the rest of the section, which is not that much anymore, will be about the matrices that induce isomorphisms. So this is what we haven't studied in detail so far, but let me erase at this point. That's a good point to stop. Let me erase. We want to consider matrices which define isomorphisms. And as we've seen before, that an isomorphism from K to N to K to M only exists if the two dimensions are the same, so if M is equal to N. Which means we only have to study matrices whose number of rows is the same as its number of columns. So we take some number n in N and take a matrix with n rows and n columns. Such a matrix is called a quadratic matrix for obvious reasons, because the rectangle that is kind of formed by a matrix becomes a square. This is called a quadratic matrix. Now, this is just a matrix which just induces a map from K to N, K to the power of N to itself. Now, if we call such a matrix invertible, if it induces an isomorphism. So if Fa from Kn to Kn is an isomorphism. Okay, and if we have a matrix B, which is also an n times n matrix, if the map induced by a matrix B, if this map is the same as the inverse of Fa, so if Fa is an isomorphism, the inverse is also an isomorphism from Kn to Kn, so it has also be induced by a matrix. So there is some B, Then we give this a new name. We put a to the minus 1. We define this, so this matrix B is called a to the minus 1 and call it the inverse matrix. Matrix of A. Okay, and yeah, keep in mind, not every every matrix of this form induces an isomorphism. For example, A could just be the 0 matrix, where every entry is 0. So this map FA would also be just a map which maps everything to 0, which is certainly not an isomorphism. So not every map has such an inverse. So not every such quadratic matrix has an inverse. So we really have to pay attention to which ones we have. Now, if we define G, L, and K to be the set of all invertible matrices in Mn times n, K, A is invertible. So we call this GL and K and call this the general linear group over K. Linear group of degree n over K. So general linear group. If this sounds familiar, recall that we already defined the general linear group of a vector space, which consisted basically of all isomorphisms, sometimes seen as maps. So this would be kind of since we have seen that linear maps can be interpreted as matrices and so on, this would correspond to the general linear group of the vector space K to the n, which would in matrix terms be the same as this. So this is what we call it. Now, this is called group for a reason. And this is what we want to study. We want to study basically that this together with matrix multiplication becomes a group again. So becomes, not again, but becomes a group. Okay, first of all, how to find out if a matrix is invertible. Just keep in mind that we have seen this so far. We have seen in theorem 8.8 in this video in the beginning, 8.8c, we've seen that the map of that a matrix induces is an isomorphism if and only if the columns are a basis. So by theorem 8.8c, A is invertible if and only if the columns of A form a basis of K to the n. Again, up to identifying column vectors with points in Kn, of course. Okay, so this is just how we can find out if a matrix is invertible or not. Now, theorem 8.15. Oh, something I wanted to mention. So if a matrix induces an isomorphism, we know that we have some inverse, but so far there's no direct way of computing this inverse. We will later see how we can compute this. If A is a given matrix where there are really numbers in there, that we can compute the inverse then. But this requires some more theory and some more further techniques that we haven't established yet. So this is what we will see later on in this lecture, but we will learn about this and we will compute inverse matrices. So this will be possible. That's the good news. Okay, let n be some natural number. First of all, if A is an invertible matrix of degree, is in the general linear group of degree n over K, so it's an invertible n by n matrix, then the inverse matrix does what an inverse should do to earn its name, namely A times A to the minus 1, so this is really the matrix product we had in this lecture, in this video, is the same as A minus 1 times A is the identity matrix of degree n. So this is kind of, yeah, if you think about the very beginning of the mathematics 1, where we had groups and so on, this is basically what a group inverse element in a group should do. So to earn its name group, this is something that we really need in there. So this holds, and something else which is interesting, the inverse of the inverse of an invertible matrix is, again, the matrix itself. Okay, B, if we have two invertible matrices, A, B in G, L, N, K, then the product is invertible. So A times B in G, L, N of K. This is also good for this idea that we want G, L, and K to be a group, because of course the product needs to be in there. Otherwise, it doesn't make sense to talk about this. So then A times B is in there, and we can compute the inverse as follows. A times B to the minus 1 is the same as B to the minus 1 times A to the minus 1. Actually, if we would have already shown that it's a group, we could then use this and derive this from the group properties, but I want to do this once explicitly so you see what's going on. So these properties of invertible matrices on multiplication we are going to show. So, part A. Again, we know that the product induces composition. So same argument as before, so by theorem and definition 8.9. So we see that the induced maps are A times A minus 1 induces FA composed with the inverse of A simply by definition of this inverse matrix. The other product, A minus 1 times A, induces F A to the minus 1 composed with FA. But this is, of course, a map composed with this inverse, which is just the identity. But, FA composed with FA minus 1 is the identity on k to the power of n, which is the same as the other composition, since it's the same space. So they are both the identity. And surely this then implies, just by uniqueness of the matrices again, A times A to the minus 1 is equal to A to the minus 1 times A is equal to the identity matrix of size n. Since this matrix, of course, induces the identity here. And so this is the first part, and the second part that I had in there was that the inverse of the inverse is the matrix. So the second part follows in the same way. I don't want to go into detail here, but follows from the obvious fact that if you consider the induced maps, if we take the inverse of the inverse map, just by definition, this is simply FA. So if we again consider the induced matrices, then we get the equality that we wanted. The matrices which induce these maps, we get the equality we wanted. Okay, B, same way. So A and B are invertible matrices, which means that FA and FB are isomorphisms. And we've seen that the composition of isomorphisms is an isomorphism, so FA composed with FB is an isomorphism. And this means that since this is then by this theorem, I don't write this down every time I use it, but by this theorem, this composition is induced by the matrix product, so this matrix product is invertible. So in GL and K. Whoops, okay. And so A times B to the minus 1, so just to get the formula for the inverse, this induces, so the map induced by A times B, so FA composed with FB to the minus 1, so the inverse map of this. But we have seen for maps that we have this relation, the inverse of a composition is the composition of the inverses, but the other way around. This is just by properties of maps. So this is induced again by this theorem, so the product of the two, and this is B minus 1 times A minus 1, which is induced by this. And so this means that this matrix is the same as that, and this concludes the proof. Okay, so this is just standard properties of this multiplication for isomorphisms, and we get a nice corollary of what we have done so far, namely we get the group property, and this doesn't require much proof anymore. So, GLNK, together with matrix multiplication, is a group for each n in n. Okay, so first of all, we need to see that the multiplication is well defined. And this is what we just did. We saw that the product of invertible matrices is invertible. So the multiplication restricts to a map which is just defined on the set of invertible matrices. So by theorem 815b, the product restricts to a map which takes, so let me just write this in this strange way, which takes two matrices, so a GLNK element times another GLNK element, and spits out an invertible matrix. So this multiplication is well defined if we just restrict to GLNK. Now, as the associativity of matrix multiplication is what we have proven. Is this, oh no, this is not in here anymore. No, this was in the previous blackboard, but the associativity of this, and existence of neutral element, which we have in the group, which is the identity matrix in this case. So this is the identity matrix of size n. This was part of this one theorem where we just showed that this must the multiplication is associative, and multiplying with identities doesn't change anything. So this was theorem 812. This holds by theorem 812. And so we have associativity, we have the existence of a neutral element, and the third ingredient that we need for a group is the existence of inverses, while existence of inverses, and by this time I mean, so I called this inverse matrix without caring for this, but we have seen that the inverse matrix I have defined as really the inverse element here with respect to the matrix multiplication. So existence of inverses, inverses follows from theorem 815a. So we have now defined a group of matrices. We will see more groups of matrices in a bit, but this is kind of the first important matrix group. Okay, so this finishes this section. So we've seen now really that matrices and linear maps between spaces of the form k to the n are basically the same thing. And we have studied the behavior, and we kind of saw that the multiplication of matrices is the analog of the composition of maps in this linear world. But that's not the end of the story, because in the next section we will then study much more general vector spaces. We will see that we study maps between finite dimensional vector spaces, and we saw that each finite dimensional vector space is isomorphic to k to the n, where n is then the dimension of the vector space. This is what we've seen, and with the help of such isomorphisms, we can also describe linear maps between arbitrary finite dimensional vector spaces with the help of matrices. This will take some more work, and this will be the main content of the next section. See you then.